All right. All right. Good morning. So, how was the weekend? Any questions? Any quick questions on the homework? Anything you want to talk about? Okay. Before we get started then, there's one quick thing I want to address because that might be important for the future. Okay, we do that, and then we do this. Okay. So, just a quick reminder, make sure to be aware of this webpage because it will be updated frequently. So basically, this is Pavel's personal webpage for Math 16020, so that's going to have quite a few things. So basically it has a lot of basic information. And if you scroll down, here are all the templates for each individual lesson. So for here we have the individual blank outlines that we fill in during class, and then after class they will be put here, and then the corresponding YouTube video will be put up on the third column. So that will be one of the recorded lectures, and that will be put there. Okay? Just a quick heads up on that. And if you guys would like to take a quick little screenshot of that URL up there, it's based, or you could also just go to the Math 16020 course webpage, look up Pavel's name, and if you click on that, that will help link directly to the websites. Okay? Or I'll just show you as such. So, what I mean is we scroll down, this is the page, we click Pavel's name, here's this home page, so you click that. So, you scroll down, and then the only thing you need to worry about is this link right here, which will direct you to this. Okay, just a quick little reminder on how that works. Alright, so, a couple quick announcements. So quiz 1, as I've been mentioning, lesson R is going to be today at the end of lecture. And quiz 2 will be this Friday, covering lessons 1A from last Friday, and then 1B, which is today's lecture. Alright, so, let's talk about the warm-up problem, shall we? So, for those of you that did the warm-up, what did you guys get for your antiderivative?
I got 2/3 the square root of 3x plus 4 plus c.
Perfect. Alright, so let's talk about why. So in this case, the problem says use the appropriate substitution. So in this case, you would let u, in this case, equal the linear expression as per our rule from last time. So let u equal 3x plus 4. So then in that case, we say, alright, that means du equals 3dx, because the derivative of this guy with respect to x is just 3 as a linear function. So then if we solve for dx, we end up with du over 3. Okay? So then, we say, alright, we have 1 over the square root of 3x plus 4 dx is equal to 1 over the square root of, well, 3x plus 4 is u, and dx is this guy right here, so du over 3. So then we can then rewrite this integral here as we have 1/3 times 1 over the square root of u, so that's the same thing as u to the power of negative 1/2 du. Okay. So then applying the antiderivative power rule will then yield us, let's see, that would be 1/3 times 2 to the times 1/3 times 2 to the power of 1/2 plus c. This is just a quick application of the antiderivative power rule. So, in this case, remember, our final answer needs to be in terms of the original variable here. So we have, in this case, we must have 2/3 times u, which is 3x plus 4 to the power of 1/2 plus c. Okay? So, just a quick little refresher from last time. So, Nothing too crazy so far, so any questions on that? Okay. So, with this next example here, I see some of you starting to work on it a bit already, so I'm going to stop you right there before we go too far. So in this case, we have evaluate the definite integral from 4 to 15 of the same function. Now, here, well, I'll go ahead and write that here. So definite integral of the same function. Okay. So the thing is that while you could say, all right, well, I have the antiderivative, so just apply fundamental theorem from there and I'm good, right? Well, you can do that. So can apply fundamental theorem of calculus from above antiderivative. So what I mean by that is we say, all right, so the integral from 4 to 15 of 1 over root 3x plus 4 dx. We say, all right, well, we have the antiderivative, so all we have to do is just say, all right, well, we have 2/3 times the square root of 3x plus 4, and then from 4 to 15, and then you go from there, right? So you could do that, and that's totally legitimate. But let's try something else. But let's try another trick. Okay? And this trick is going to be generally quicker. So in this case, we change bounds with the U substitution. Okay? And the reason I'm encouraging this is because this is generally quicker. Okay? So here's what I mean by this. So because we're working with the same function here, well, that should naturally tell you the same U substitution must be applied, right? So, taking that U substitution from up here, we say, all right, let's go ahead and use this substitution to change these bounds here. So here's what I mean. So we have x equals 15 and x equals 4. So from here, we say, all right, we have if x equals, say, 4, then we want to be able to translate this into the corresponding u value. So in this case, since u equals 3x plus 4, we just have to let x equal the whatever bound we have into here, and then that'll be the corresponding u value. So in this case, we have 3 times, well, in this case, 4 plus 4, and a quick bit of algebra should tell you this is just 16. Okay? And then do the same thing with the other bound, so 15. So all we have to do is just replace x here with 15 as per our substitution. Add 4, and then a quick bit of algebra should tell you this is just 49. Okay? So now what this says is, okay, so we have integral from 4 to 15 of 1 over root 3x plus 4 dx. So regarding everything that's going on here, nothing changes from the warm-up. So ultimately, you're still going to end up with this guy right here, what we have from the warm-up. So I'll go ahead and write that down. So we have 1/3 times u to the negative 1/2 du. So nothing there changes. But because now we're working with in terms of u and du, that means our bounds must also be in terms of u and du as well. So what that means is that now we're going from, instead of 4 to 15, we now have 16 to 49. Okay? So this gets changed to the corresponding u value, and 4 gets changed to its corresponding u value. Okay? Okay, so that's the idea behind that. And the reason we're doing this is to say, okay, once we evaluate this integral, because we're just looking for the numeric value of the original integral here, once we solve this, we're done. We don't have to switch back to x on it. So, in doing so, we say, all right, so we still have, you know, if we keep everything in terms of u here, well, we still have 2/3 times u to the 1/2, as per we have up here. Except now we are going from u equals 16 to u equals 49. Right? Okay. So then if we apply the fundamental theorem of calculus from that, we can say, all right, this is just 2/3 times 49 to the 1/2 minus 2/3 times 16 to the 1/2. Okay? So if we simplify this down a bit, then what should be our final results? Yeah, just 2, right? Because this is just 2/3 times root of 49 to the 1/2, that's just 7. And then minus 2/3 times 16 to the power 1/2, well, that's just 4. So simplifying all that down will pretty nicely get you the nice value of 2. Okay. So any questions on any of that? Okay. So I'm just going to scroll this up a bit. So is anyone still writing this down?
So I see what we're doing. We just, instead of substituting u for the original equation, we're substituting just the numbers that we got.
Yeah, so we're substituting the bounds, and that way we can say, once we evaluate this integral, which we did here, then we're done. We don't have to switch back to x at all.
Okay.
Any other questions on that? Okay. So let's move on a bit to our next example. So the premise is, suppose a strain of bacteria initially has 20 bacteria present in and the number of bacteria n of t at time t has a rate modeled by t over the square root of 3t plus 4. So in this case, what that means is that because this n of t has rate modeled by this, that should tell you, because of the rate, assume that this will mean that this will give you n prime of t. Okay? So, well, the question is, how many bacteria are present 3 seconds later? So we need to run to the nearest number of bacteria. Okay? So now let's take a look at what we're given and what we need to find. So we're given, so n prime of t, as we just stated, well, it's equal to this, 3t plus 4. And we're also given an initial data point, right? So the strain of bacteria initially has 20 bacteria present. So as per what we talked about last time, that means that the number of bacteria is 20 at what time? 0. Good. Because remember, whenever you see like initially or starting with or anything like that, that should be a really good indication that you have to be working with t equals 0. So t equals 0. Okay. So this is what we're given. So based on what the problem's asking, what are we trying to find? We need to find what numerical value? Got to find n of 3, right? And so we have to find the number of bacteria modeled by this function here at time 3. That's the whole goal of our problem. So you might think, all right, well, I can just use a initial value problem because this is set up very much like one, which you can do. So can use an IVP, initial value problem, but we're going to try another trick that might be a little bit quicker. But let's instead use fundamental theorem of calculus, just as another way of being able to attack this problem. So if you recall, we have a function, and we have two numerical values where we need to work with. So what I mean by the fundamental theorem of calculus is to say, all right, we have n prime of t, which if you just integrate this by itself and move on, then we'll get the general solution, at which point you can use this to get the particular solution. Use this initial data point to get the particular solution. But the thing is that we need to be working with the number of bacteria at times 0 and 3. So what we can do instead is say, all right, well, let's work with the times 0 and 3, and say, okay, well, by the fundamental theorem of calculus, well, this is just the difference n of 3 minus n of 0, right? So we're given this, and, well, we can find this using the necessary substitution. So all we need to do is say, okay, that means n of 3, this value we're looking for, is just equal to n of 0 plus the integral from 0 to 3 of n prime, which is given by this function here, which is t over the square root of 3t plus 4 dt. So, like we said, we already got n of 0, so once we figure out this integral here, then we're done, essentially. So, let's go ahead and do that. So let's go ahead and solve for this integral and see what we get out of this. So, going from 0 to 3, and then t over the square root of 3t plus 4 dt. So, based on what's going on here, what do you think would be a good use substitution? Go ahead.
3t plus 4.
Okay, let's use 3t plus 4. So, in this case, we have u equals 3t plus 4. So that means du by similar reasoning, that means du by similar reasoning as the warm-up would have to be 3 times dt, and consequently, dt would have to equal du over 3. Now, we will have to change the bounds, but let's focus on just the integral for a bit, because there's something you might notice. What you'll notice is that, all right, we have t over the square root of, well, u, because that's what 3t plus 4 is equal to u. And then we have du over 3. Okay, well, now we have a problem, because we still have this t hanging out here, and it doesn't really seem like there's any way we can get this to cancel from just here. But if you take a notice, you realize, wait a minute, u and t seem to satisfy a linear relationship here, don't they? So, what do you think would be a good workaround for this?
Find a way to have t equal to an equation with variable u.
Exactly, we need to solve for t here, right?
Yes.
So, if we solve for t in this equation here, then what should we get? Let's give someone else a chance.
U.
Yep, u minus 4 over 3. And then that equals t. So now we can express t in terms of u, so that'll give us a way to circumvent the problem. So now we have, all right, this is t here, so we can just let t equal this expression in terms of u, and then that's our problem solved. So we have, in this case, u minus 4 above here, and then we have over 3, but then we have a divided by 3 down here as well. So ultimately, we're just going to have 9 times the square root of u. So we have, basically we're multiplying this 3 here with this 3 here. That's how we get it. Okay? And then d. So thankfully, now we have a way to fix the problem and get everything in terms of u. So now let's go ahead and change the bounds from this. So that means we have t equals 3 and t equals 0. So if t equals 0, then that should indicate that u should correspond to what value? Yeah, it's 4, right? Because in this case, we're just letting t equals 0 in our given substitution up here. So plus 4, and then that equals 4. And then similarly, the corresponding value of u for t equals 3 should be what? Yeah, 13, right? Because 3 times 3 plus 4 is 13. So that allows us to change the bounds. So now we have, going from 4 to 13 is our new bounds. So from 4 to 13. Okay? So now all we have to do is evaluate this guy, and then we're done. So let's go ahead and do that. So what I'm going to do is I'm going to take this this factor of 9 downstairs. I'm going to throw that outside, just so that way it's not in the way of anything. So I'm going to throw this 1/9 outside the integral. So then if we just focus on this guy right here, I'll just put this in red so that way it's a bit clear what I'm talking about. So that means that the expression in red is the only thing that's left inside the integral. So now we have to figure out how to express this in a way that allows us to take its antiderivative. So how do you think we could do that? Let's give someone else a chance.
Split the fraction.
Okay, split the fraction as what? So we have, in this case we have u over the square root of u, and then 4 over the square root of u, right? Okay. So then, using exponential properties, we have 1/9 times integral from 4 to 13 of, well, in this case we have u to the power of, the first term is u to the power of what? 1/2. Okay. Good. And then similarly, we have the second term is just 4 to the power of times u to the power of -1/2. Right? Okay. So then if we apply the fundamental theorem of calculus on this, we say, all right, now all we have to do is apply the antiderivative power rule. So, well, if we apply the fundamental theorem, sorry, not the fundamental theorem, not yet. If we apply the antiderivative power rule on the two terms we have, what should we get? Go ahead.
2/3 u to the 3/2 minus 8 u to the 1/2.
Yep. So 2/3 times u to the 3/2 minus 8 times u to the 1/2. And then, again, this is going from u equals 4 to u equals 13. Okay? So from here we go ahead and apply fundamental theorem of calculus, and then we move on. So here we have 1/9 times 2/3 times 13 to the 3/2 minus 8 times 13 to the 1/2, and then minus 1/9 times, well, do the same thing with the lower bound. So in this case, we have 2/3 times 4 to the 3/2 minus 8 times 4 to the 1/2. So that, and then, okay, good. So what I'm going to do for now is say, okay, once you plug all this into a calculator, this is going to give you the somewhat anticlimactic value of 1.45. And the reason I say this is anticlimactic is because, well, if we look back at the original problem, the problem says we need to figure out how many bacteria are present 3 seconds later. And we need to round to the nearest number of bacteria. So from this, we say, all right, going back up here, ultimately we have to figure out n of 3. So we say, all right, now that we have the value of the integral, we say, all right, we have n of 0, which we established to be 20. So 20 plus 1.45, so that's 21.45. But rounding to the nearest number of bacteria, well, that's just 21. So basically what we're saying is 3 seconds later, we gain a whopping 1 whole bacteria. Yeah, all that work just to save one additional bacteria. That's all we get. Well, it's a little anticlimactic, but if you increase the number of seconds, you eventually realize, okay, it does get bigger, but the rate is just kind of slow. So that's why we don't have a lot of bacteria. Okay, yeah.
So for n of 3 with 20 plus 1.45, I know where we got the 1.45, but I know the 20 is the 20 bacteria. That's n of 0. How did you get like that whole equation?
Because of this guy right here. Because fundamental theorem of calculus, remember?
Right. I'm saying I know that part, but are we just doing that plus
Yes.
n of 0?
Yes.
Okay.
Yeah. All I do is just add n of 0 to the other side to get this.
I got that.
Any other questions? Okay, cool. So now let's move on to the last two examples I have. So moving on to example 3. So we have that the area of the region under this curve, 10x plus 5 times x squared plus x to the power 4. It's bounded. We have this region bounded above by this and bounded by x equals 0, y equals 0, and x equals a. And we're assuming a is greater than 0. And we have to say that, all right, this whole area is 32, and we have to figure out the exact value of a. Okay? So let's give a quick recap as to what's going on here. So does anyone still need page 2? So here's what's happening. So if you recall from lesson R, so in this case we're going from x equals 0, so right here, and to some x equals a. And in this case we can say, all right, just by looking at this, we can go ahead and assume that this is greater than 0, so you're going to have some function that looks like this. And we're assuming that the area of this region here is 32. So area of this guy is 32. Okay. Now, if you recall, if you recall from lesson R, what is the integral that we need to work with here in order to be able to find the area of this thing? If you recall from lesson R. So we have the integral, we have this function from x equals 0 to x equals a, and remember, y equals 0 is the x-axis, right? So, do you guys remember from lesson R what the integral should be? Yep. So the bounds are going from 0 to a, because that's upper, this is lower and this is upper bound. And then what's inside the integral? What function do we have that should be plugged into the integral? Yep, this whole thing right here, right? So we have 10x plus 5 times x squared plus x raised to the power 4 dx. Okay? And the thing is that we're assuming that since this corresponds to the area of our region, that must mean that this is equal to 32 by assumption, right? So all we have to do now is just figure out what the heck is a. So that's all we got to do from here. So we solve for a, solve for a. So from here, based off the title of today's lesson, well, what should that tell you about the trick we need to use here? So because we're working with substitution, what should that tell you about what our substitution should be in this context?
It should be x squared plus x.
Yep. You should equal x squared plus x, right? Based off the fact that this is one function within another. And so that would tell you, all right, well, du should be, well, a quick application of power rule should then tell you this is just 2x plus 1. And then so dx should then be du over 2x plus 1. Okay? Nothing too crazy. But we also need to change the bounds as well, right? So we also need to take into account, so if x equals a and x equals 0, then we need the corresponding u values, right? So if u equals x squared plus x, well, if we just let x equals 0 here, well, that should pretty quickly get us 0. No problems there. But then the only thing we can really do with this is say, all right, well, if we let x equals a, the best we can do is just a squared plus a. That's the best we can do. Okay. So from here we say, all right, going from 0 to a squared plus a. So we have 10x plus 5 times u to the 4th, and then times du over 2x plus 1. So we have integral from 0 to a squared plus a. So if we take a look at these two expressions here and see how they simplify, well, what would you end up with in that case? So in other words, how does 10x plus 5 over 2x plus 1 simplify? Well, not quite. So if we take a look at these two terms here, right, they both have a factor of 5 in them, right? So if we factor out that 5, what do we get out of that? 2x plus 1, right? So that should tell you that this divided by this is just 5, right? So then we have 5 times u to the 4th du. Okay. So then a quick fundamental theorem of calculus, antiderivative power rule application should then tell you that this has antiderivative u to the 5th, going from 0 to a squared plus a. So now we apply a fundamental theorem of calculus, and then you realize, all right, this is just a squared plus a to the power of 5th, and then, well, minus 0 to the 5th. So ultimately, this is just what we get from the fundamental theorem of calculus. So now we got to solve for a here. So now we have to bring the fact that this is equal to 32 back into play. Okay? And what happens from here is now we just solve for a. So if we note that if we note the fact that this is raised to the power of 5, then what can we do with both sides to remedy that?
Take the 5th root.
Yeah, take the 5th root, right? So if we take the 5th root, then that means that the other side here is essentially going to be the 5th root of 32, which simplifies to 2, right? So then what you also notice is that if we subtract this over to the other side, this 2, then, oh wait a minute, we got a quadratic equation, don't we? So, if we factor it out, and if we factor this equation, then that means we should end up with what two values of a as our potential candidates? Yep, -2 and +1, right? If we factor it out. But then you realize, oh, wait a minute, our assumptions say that a has to be greater than 0, so that's out. This -2 is gone. So rather anticlimactically again, a has to equal 1 here. And that's example 3. Yeah. Again, all that work just to get the fact that we get 1 as our answer. Yeah. Okay. Okay, so any other questions on this one? Alright. So, let's see. Let's go ahead and look at one last example here. So, we're looking at the velocity, v of t, of a particle moving along, this should be x-axis, sorry for the typo, is given by this velocity equation here. And if the particle starts at 11, we need to find the position at time t. So, if you recall from Calc 1, what's the relationship between velocity and position functions?
Velocity is the derivative of position.
Yep. So we have s prime of t is equal to v of t, right? So here's what it says. So we have S prime of t is equal to negative 3t times sine of t squared. But then we're also given the fact that the particle starts at 11. So that means, well, as per what I've been establishing until this point, that means the particle has position 11 at time 0. Good. Okay, so here's what we're given. Again, another initial value problem. So then that should pretty quickly tell you, well, we need to figure out, all right, well, what's the position function? But thankfully, that's exactly what the problem wants us to find. So once we find S of t, then we're done. So that implies that S of t, so if we find the general solution first, we just have to take the antiderivative of S prime, so just negative 3t times sine of t squared dt. Okay? So if we do that, then what would our u substitution from this be? Okay. Yeah, just t squared, right? So that's equal to u. And then from there, we'll just say, okay, I'll just skip an extra step and say that in this case you should end up with the fact that, well, if you take the derivative and then solve for dt, you should end up with du over 2t. Okay? So doing that, we end up with, well, negative 3t equals sine of u times du over 2t. So what you notice is that the t's cancel each other out. And so we end up with, well, negative 3 halves times sine of u du. So this is going to have what as its antiderivative? Yeah, just positive cosine, right? So we have, in this case, we have 3 halves, positive 3 halves times cosine of u, and then plus c, of course. So then our general solution, therefore, becomes 3 halves times cosine of t squared plus c. Okay? That's equal to the general solution. So from here, we say, all right, now we have the general solution, so now we just use our initial data to figure out, well, what the heck is our c constant equal to? So we have s of 0 is equal to, so if we let t equals 0 as per our initial data, we have 3 halves times cosine of 0 plus c. So if we simplify this, well, we note that cosine of 0 is equal to what? Yeah, just 1, right? So ultimately we have 3 halves plus c is equal to, by assumption, 11. So that means that c is equal to what fraction?
22 over 3.
Wait, 22 over 3? Remember, we need some, this is 3 times plus c. Should be, so in this case you should end up with something over 2. 19 halves, good. Okay? So, ultimately, you should end up with the particular solution of s of t is equal to 3 halves times cosine of t squared plus 19 halves. Okay? And that's your particular solution that you need. Okay? Okay, so any questions on any of this? Okay, well, that's all I had for the lecture part of this lesson. So let's now move on to the quiz part of our section today. So, premise is that now, so what we're going to do is when you're done with your quiz, raise your hand and then place your quiz face down and then raise your hand and then I'll come pick it up. So, sound like a plan? Cool. Make sure to have a one-line calculator. And I will come around and be like, okay, if I see a one-line calculator, if I don't see a one-line calculator, I'll be like, that's a 2-line calculator. There's 2 lines to it, so it's 2 lines. So thankfully, you don't really need the calculator for today, but it will kind of help. But in any case, here's the quiz.